You know how to represent the structure of a molecule with a Lewis structure. You know how to determine shape using VSEPR theory. You know how to use electronegativity, bond polarity, and shape to determine the polarity of a molecule. In this video, we'll use polarity to determine intermolecular forces to explain properties of substances. So far, we've looked at strong chemical forces. Those are the interatomic forces which holds atoms together to form compounds. Ionic compounds are held together by ionic bonds. Molecular compounds are held together by covalent bonds. The weak chemical forces are the intermolecular forces. London forces exist in all substances. Dipole-dipole forces exist between polar substances only. Hydrogen bonds are a special type of dipole-dipole force. A hydrogen bond exists when a hydrogen is situated between two very electronegative atoms on two different molecules. The weak intermolecular forces hold atoms and molecules together in its gas, liquid, and solid states. Oxygen and sulfur are found in group 6 in the periodic table. But why is water a liquid and H2S a gas at room temperature? We can explain using intermolecular forces. Stop the video and review these steps to determine the intermolecular forces in a substance. So here's the Lewis structure of water. The shape at the oxygen is bent. The polar OH bonds in the bent shape make water a polar molecule. So there will be London forces and dipole-dipole forces between water molecules. Now look at these two water molecules. There's an H between two very electronegative oxygens on two different water molecules, so that's a hydrogen bond. So stop the video and determine the intermolecular forces in H2S. And here are the answers. Just like water, H2S is a bent shape and is polar. But this is not a hydrogen bond. Sulfur is not a very electronegative atom like oxygen is. So at room temperature, water is a liquid and H2S is a gas. Water has all three intermolecular forces, whereas H2S only has London forces and dipole-dipole forces. This means more energy is required to break the strong intermolecular forces between water molecules, and this results in a higher boiling point for water. Let's look at the intermolecular forces in CO2. Stop the video and review the structure, shape, polarity, and intermolecular forces in CO2. These lone pairs are missing from CO2. Is CO2 soluble in water? Stop the video and think about that. And the answer is, since CO2 is nonpolar, the intermolecular forces between CO2 and water are London forces only. Acetone is a common organic solvent. It's used in fingernail polish remover. Is acetone soluble in water? Stop the video and determine the structure, shape, polarity, and intermolecular forces in acetone. And the answers are there any hydrogen bonds between acetone molecules? Draw a second acetone molecule and find out. The circled H is situated between an oxygen and a carbon. Carbon is not a very electronegative atom, so there's no hydrogen bonds between acetone molecules. Acetone and water are polar, so acetone is soluble in water. The intermolecular force between acetone and water can be London forces, dipole-dipole forces, and hydrogen bonds. Hydrogen bonds are very important in biology. Stop the video and determine the chemical force in each blank in this protein. And the answers are, in a hydrogen bond, the very electronegative atoms that sandwich the H are oxygen, nitrogen, fluorine, and chlorine. One way to denature a protein is to heat it up. Stop the video and figure out what chemical force is going to break first. And the answer is, here's the pan-C enzyme. Note that the alpha helices and beta-pleated sheets are held together by hydrogen bonds. In your favorite red or blue or green shirt, chemical forces are involved between dyes and fabrics. Fastness and levelness are two properties of dyes. You want your blue shirt to stay blue after repeated washings. You also want your shirt to be uniformly blue through the entire shirt. Blue jeans might just be the world's most popular piece of clothing. The water-soluble form of indigo is yellow. The water-insoluble form of indigo is blue. Note the slight difference in structures. Indigo dyes cotton, so stop the video and figure out the chemical forces that bind indigo to cotton. And the answers are, the bent shape at O and the trigonal pyramid shape at N make those parts of cotton and indigo polar, therefore dipole-dipole forces. And there's also extensive hydrogen bonding. Note the hydrogen situated between two very electronegative atoms, oxygen and nitrogen, on two different molecules. Textile production involves a lot of chemistry. Over 8,000 chemicals are used to make 400 billion square meters of fabric each year. 1,800 gallons of water is required to make one pair of blue jeans. Another dye is picric acid, although its primary use is as an explosive. Stop the video and identify the chemical force that binds picric acid to wool. And the answer is, a proton is transferred from picric acid to wool in an acid-base reaction. Two ions form, so an ionic bond forms. One dye does not work for every fabric, so this table shows the different dyes used for different fabrics. Dyes and pigments are also used in printers. Has anyone gone to the paperless office yet? Chemical forces bind the ink to the paper, but during recycling, how is the ink removed? Hydrogen bonds that break and reform cause wrinkles in shirts. In permanent press shirts, a chemical links cotton chains together to prevent wrinkling. Stop the video and identify the chemical force involved. And the answer is, I'd never have to iron again. Just like cotton can link together, so can hair. Where the crosslinks form determine whether your hair is straight or curly. In personal care products, silicone compounds give skin creams a silky, non-greasy feel and hair a luxurious bounce and shine. In medicine, most drugs bind to protein targets via weak intermolecular forces. New drugs are being developed which form stronger covalent bonds to proteins. This leads to higher selectivity and low toxicity.